Hello everyone, and welcome again to 3D Experience World 2021. Nandish and I are excited to present best practices for solving large assemblies in SOLIDWORKS Simulation. If you're looking for game-changing techniques, you are at the right place because we're going to give 20 great tips on how to make the most out of SOLIDWORKS Simulation. My name is Maidwan, and I'm the product manager for SOLIDWORKS Simulation.
Hi everyone, I'm Nandish Datti, working as product definition manager for SOLIDWORKS Simulation and SOLIDWORKS Plastics.
To tackle the topic of large assemblies, I will start with tips and tricks on geometry preparation. Then Nandish will tell you about important improvements to contact, which is now known as interactions. After that, I will show you how to set up for a successful mesh. Then finally, Nandish will give you recommendations on solvers. Isolate subassembly. We are going to use this Resin Bolter 77 tractor as a case study to make our point. So, for example, when this tractor is working 1,000 feet underground, it is critical that every component works all the time. Let's think about the boom. If it doesn't work, none of the other part matters. No boom, no operation. Lives are put at risk, capital sits idle, and money is lost. So how do we make sure this boom works all the time, every time? That's where simulation comes in. We can try to simulate all 5,000 parts in the tractor, but that would tax any simulation software beyond its limits. So the solution is to isolate and analyze critical sub-assemblies, in this case, the boom. Before you analyze, you have to prepare. Preparation could include use configuration, symmetry, remove unnecessary components, suppress cosmetic features, address interferences, choose element type. This preparation is the difference between getting results quickly and being stuck with errors and frustrations. Configuration and symmetry. Let's look at how configuration can be used. I am creating a new configuration called simulation, which I can use to make modifications for simulation and not affect the production model. Here, I created another configuration for sim called FEA symmetry, where I only use half of this boom for analysis. The concept of symmetry is very simple. It can dramatically reduce the model size and therefore speeds up solve time. By applying symmetry to our Resin tractor case study, I reduced the number of nodes by half. As a result, the solve time was reduced by over 50%, from 13 to 6 minutes. Next, simplified geometry. Let's talk about how to simplify. That just means removing unnecessary components. Here's an example. I'm going to remove all the screws, nuts, and bolts because we already know how they're going to perform, so we don't need to include them in our analysis. I am selecting components by size. Then click on Hide Components. Here I'm selecting identical components and then Hide Components. Now I'm selecting all hidden components and suppress them all in a single step. This is a good practice because suppress each group of components can take a long time in large assemblies. Simplify is a concept that you should apply whenever practical in SOLIDWORKS CAD. But now I want to give you a great tip. Use a feature called Exclude from Analysis, which is entirely within simulation. This is another method of preparation that you could use to remove unnecessary components, which you don't want to take into consideration in simulation. Here, in SOLIDWORKS Simulation, I select all the screws in this folder, then right mouse button and select Exclude from Analysis. The advantage of this method is you don't have to create a separate SOLIDWORKS simulation configuration. Now let's talk about the feature. The concept here is to remove cosmetic features. By definition, they're not critical. Therefore, let's not waste computing power by including them in our subassembly. Does our analysis need to include the motor number and part specifications? No, of course not. Then select and suppress. Interferences. A common situation is your assembly has lots of interferences. There are three scenarios. The first is shrink fit that Nadesh will go over in the interactions section. Second scenario, the interferences are not present in key components. You don't need the software to calculate the interactions between these components, and you just want quick results. Then you don't need to do anything. Just use independent mesh. I want to talk about the third scenario, where interferences are in critical areas, and you want to resolve them. Here's an example. I have interferences between these two components. So what I'm doing here is edit the black part within this assembly. Then go to Insert, Molds, and use the Cavity tool. I choose the metal top part as a cutting tool. And here we go. No more interferences. Element type. Be strategic in selecting the element type. Choosing the right one will save you time and lead to more accurate results. For thick and chunky components, choose solid elements. For sheet metal and thin wall parts, choose shell elements. For weldments, choose beam elements. One strength of SOLIDWORKS simulation is it automatically recognizes sheet metal parts as shells and weldments as beams. In addition, it can handle mixed meshing, which is a combination of solids, shells, and beams. Mixed meshing offers flexibility and allows you to mix and match the appropriate element type. However, make sure all your components are properly connected using the tools provided by Nadesh. So these were my top 5 tips on geometry preparation. Of course, there are so many other techniques to prepare geometry for simulation, but it is now time for me to introduce you to Nadesh. Nadesh is our product definition manager for SOLIDWORKS simulation, and he knows his stuff so well, he actually writes the specs.
Thank you, Mai. I agree with you that those are the most widely followed geometry preparation approaches in the industry. Let me talk about some of the exciting features related to interactions and share the 5 best practices. Types of interactions. We know that specifying appropriate interactions between the components play an important role to get the right behavior. While the bonded and free interactions can help us to solve the study quickly, the number of contact interactions can add complexities and increase the solving time. Hence, if you are dealing with an assembly simulation, then we strongly recommend you to start with the bonded interactions. Level of interactions. We know that the interactions can be specified at global level, component level, and local levels. If you are in an assembly context, then you can start with simple scenario by specifying bonded interaction at the global level. If required, you can add the complexities. This can help you to get the first pass results quickly. Instabilities due to gaps and interferences. In this section, we will learn various approaches to deal with the interferences and gaps. The first case here is that the interferences are not in the key areas. Let me give you a quick demo to showcase how it works in software. In this example, we can see that the meshing has failed due to geometric interferences. The interference detection tool has helped us to locate the regions of the interferences precisely. We recommend you to mesh such bodies independently to generate a successful mesh and solve the study. Note that in version 2021, the default global bonding formulation has been set to mesh all the bodies independently, which helps the designers to overcome the interferences. Let us take a look at the second case where we have intended interferences in this wheel assembly. In reality, the parts of this wheel assembly are assembled by means of a shrink fit, which means the rim is heated prior to the assembly and allowing it to return to the ambient temperature after the assembly. If you want to understand the interactions between such components, then you have to specify the shrink fit interaction type between the interfering components. You will be able to mesh and solve such simulations. The third type of interference can be due to geometrical inaccuracies. If you remember in one of the earlier slides, Mai has briefed us about how to tackle the geometric inaccuracies using the Boolean operations. Let me proceed to show you what we have in this scenario. As mentioned earlier, in this case, we have interferences due to incorrect dimensioning. You can make necessary geometry corrections in order to eliminate the interferences, thus we are able to create the mesh successfully. Gaps. As we were discussing earlier, the existence of gaps in an assembly may cause instabilities. When we try to solve the study, the solver may face divergence issues. I would say that handling the gaps is much easier in 2021. The version 2021 introduces three parameters such as gap range for bonding, gap range to consider contact, and contact stabilization to efficiently deal with the gaps. Gap range for bonding. If you want to treat the two components bonded together by ignoring the actual gap, then you can specify the intended gap value as gap range for bonding. Gap range to consider contact. In this case, you can specify an appropriate gap value to establish contact between the non-touching bodies. Contact stabilization. We know that the real-life assemblies can have many imperfections such as non-touching surfaces or clearances between the components. These gaps can make it difficult for the solver to get started. With contact stabilization, the solver can resolve instability issues encountered at the start of the solution before the contact is established. Let me show you a scenario in 2021 which illustrates how to deal with the gaps efficiently. The boom assembly from the resin truck consists of more than 100 components. I was able to mesh this assembly quickly. However, the solver has encountered an issue. When I continued to run the simulation, I could notice that the components at the middle of the boom assembly are having a rigid body motion. Using the measure tool and the SOLIDWORKS cross section, I can see that there is a 3 mm gap between the two components. I can now go back to simulation study and specify a 3 mm gap to enforce bonding between the selected components. Of course, this requires remeshing the model and rerunning the study. The result shows correct behavior of the assembly under the applied loads and conditions. To help the designers easily tackle the gaps, in version 2021, the global defaults for various gap properties are derived from the characteristic length of the respective geometry. However, the user can override these parameters as per their requirements. Interaction viewer and under constrained bodies. In this video, we can see that the assembly consists of three components. When I run the interaction viewer, the result shows that one of the body is not properly associated with the system. The under constrained bodies tool results clearly shows the availability of rigid body modes. Interaction viewer and under constrained bodies are two great tools to help our users to easily verify the regions of the model with different interactions and also evaluate if the model is sufficiently constrained. We recommend you to make use of these tools, specifically when dealing with assembly simulations. Connectors. Simulation has got a comprehensive and unique library of simulation elements called connectors. These elements will help us to bind the parts together by means of restricting certain degrees of freedom, allowing transfer of loads between the parts, and so on. Various connector forces extracted are helpful in deciding a suitable connector size. Let me show you one of the unique features available in simulation which enhances experience working on the connectors. Assume that your assembly consists of a bunch of toolbox fasteners as shown in the video. Using the toolbox fasteners to bolt connector setting, you can convert all the physical models of toolbox fasteners into simulation bolt connectors. Isn't it a cool functionality? I would say that the great advantage of replacing physical model with appropriate connector is that you no need to mesh respective parts, and it helps us to get the results faster. Let me now hand it over to Mai to learn some of the great tips related to meshing.
Thank you, Nadish. Meshing is a big topic. Without a mesh, you won't get any results, so you want to tune in here. The tips I am about to give you are better than chocolate and wine on your birthday. I could give you dozens of mesh best practices, but we only have time for 5 today. Let's start with independent and enforced common node. We all had our share of simulation assemblies not meshing. More than likely. The problem was nodes weren't matching because of gaps and interferences between component faces. Before SOLIDWORKS Simulation 2020, you had the option of using the independent or formerly called incompatible mesh to address the problem, but it was not the default. Independent mesh also fell short because of accuracy issues. Starting with the 2020 release, accuracy is no longer a shortcoming. The independent mesh is very accurate, and for that reason, you will find that it has replaced enforced common nodes as the default. Enforced common nodes was formerly called compatible mesh. In some cases, designers may still want to use enforced common nodes, and they can still do so with the toggle. As Nadish showed you in the interaction section, the toggle can be found under Connections, edit definition on global interaction, and turn on this enforced common node between touching boundaries. Next, let's talk about which measure to use. I am amazed to learn that some users don't realize we have 3 meshes. So the obvious question is when to use which. The software defaults to the standard measure, but honestly, you probably want to use blended curvature-based measure, also called BCB, and to a lesser extent, the curvature-based measure, also called CB. In the past, probably the reason you didn't use BCB is because either you didn't know about it or it was too slow. Now, with 2021 release, BCB is significantly faster and much more robust. It also uses multi-threading and parallel multi-core processing to more quickly mesh large assemblies. Let me show you how to take advantage of this great tip. The choice between the 3 measures can be found under mesh parameters. The standard measure uses a constant global mesh size to put a uniform mesh across parts. In some cases, it could mesh over small features using this tolerance value. The BCB measure and the CB measure have a maximum and a minimum element size, or a range. It will use this range to put large elements on wider planar areas and small elements on small features. As a result, you will get a more efficient use of elements and nodes. What I have found is many times I am able to get a successful mesh with BCB in cases where the standard measure failed. So we recommend you use BCB. Here is evidence of how much faster 2021 BCB measure is when compared to BCB 2020. Blue is mesh time for BCB 2020 and orange is mesh time for BCB 2021. Clearly, 2021 is much faster. Another tip you should know about is starting 2020, SOLIDWORKS Simulation allows you to mix and match draft and high quality elements. In prior releases, you have to apply draft or high quality elements to all components. But like everything else in life, one size does not fit all, and 2020 release fixes that problem. The benefit of this feature is you can reduce solve time by applying draft elements to non-important parts while retaining high quality elements for the critical components. Let's have a look at how to mix and match draft and high quality elements. Under parts, simply select the non-critical bodies, then right mouse button and choose Apply Draft Quality Mesh. You can see that the triangles next to the part names now have straight edges. After meshing, you can see the draft elements are shown in orange, while the high quality elements in blue. Notice how coarsely draft elements capture the geometries. So be careful. Draft quality element should only be used for non-critical components or preliminary studies. Mesh quality diagnostics. In 2021, we introduced a new tool called Mesh Quality Diagnostics. It identifies and isolates poor quality elements by evaluating attributes such as aspect ratio, Jacobian ratio, skewness. The benefit of this tool is it tells you what you need to fix in order to generate high quality elements. High quality element means faster solving time and more accurate results. Let's see it in action on this resume boom. When activating the Mesh Quality Diagnostics, you can choose an attribute such as aspect ratio. The software isolates, lists, and shows the location of the poor quality elements based on that attribute. Select the Mesh Helper and you will be prompted with suggested element size. There are a number of choices you can apply to improve your mesh quality, but for now, just know this is where you find it. Mesh failure diagnostics is a handy tip you will want to know about because it can point to why your mesh failed. How convenient is that? Let's have a look. When you open the Mesh Failure Diagnostics, it will list the bodies, faces, and edges which fail to mesh. You can go to Mesh Control to reduce the element size so they fit within the geometries, which is likely to fix the mesh failures. And now we have a successful mesh. So there you have it, 5 great tips to get you up and meshing with your large assemblies. Back to you, Nandish.
Thank you, Mai. I loved those enhancements related to blended curvature-based measure in 2021. Those tips related to meshing are very promising. Now I'm happy to share more recommendations pertaining to solving a study. Solver selections. We know that solver selections plays an important role in getting the results faster and more accurate. As some of you may know, a lot of parameters needs to be considered while choosing the right solver for a given study. SOLIDWORKS Simulation has got 5 solvers. However, one of the common questions heard from many designers is that which solver I should use for my study. We recommend you to use the automatic solver to get precise advice on the optimum solver. Some of you may be wondering, why am I advising the automatic solver here? The reason is simple. In 2021, the algorithm used for automatic solver selection has been enhanced significantly, which ensures an optimum solver for a given study. The improved automatic solver selection algorithm selects the right solver for you based on various parameters such as the number of equations in the study, available load cases, type of mesh used, available memory, and so on. The automatic solver selection in 2021 is so efficient that whether your model contains degrees of freedom under 100,000 or about 10 million, you can be confident of using the automatic solver. Simulation Evaluator. It is fairly a new feature in SOLIDWORKS Simulation with great benefits. It saves a lot of time for us by reporting the issues associated with critical areas such as disk space, material properties, quality of the mesh, etc. before solving the simulation. Raising flags for the result file path located on a network drive, low disk space, bodies that require material assignments, materials with wrong Poisson's ratio are very helpful in identifying the issues at the early stage and make necessary modifications before solving the study. This can certainly save you a lot of time associated with troubleshooting the issues. We recommend you to run through the simulation evaluator to determine whether the study setup is optimal before running the simulation. Remote load mass. This feature can save you a lot of time when used wisely. As shown in this example, I can easily replace the crank assembly, which is not the main focus in this simulation, using an equivalent remote load mass feature. As we are replacing the crank assembly using a remote load mass, we no need to mesh and solve these components. Hence, we are saving a lot of time. Using weak springs. Sometimes we spend quite a lot of time to fix the instabilities even during the first pass simulation. As part of the interactions, we have already learned few approaches to deal with the instabilities. However, if your assembly is having a lot of instability issue, then we recommend you to turn on the soft spring setting available in the study properties. This can certainly help you to prevent the instabilities. Do visit the study properties in order to activate the same. Result file size. Most of us will admit that the result file size plays a critical role. As the complexity increases, the file size can grow significantly. It is important to take necessary precautions while dealing with large assembly simulations, else you will run out of disk space. From a simulation perspective, if you are looking for displacement results only, then it is important to turn off the stresses and strains checkbox located under the result options property manager. This can avoid low disk space issues and also keeps the result file size optimum.
There you have it. 20 best practices to handle large assemblies like a pro. Today, we use resume to make our point that SOLIDWORKS simulation can handle large assemblies, but you need to know. It is a software of choice for GE, IKEA, Google, LG, Ford, Caterpillar, NASA, US Navy, General Atomics, Dynetics, and so many more leading-edge companies. If all of these companies are using SOLIDWORKS simulation to drive innovation, quality, and profitability, don't you think this is a good time to explore what it can do for you? Contact your value-added reseller today